So to go to 100 miles is 100 times more difficult. How much more difficult? How much more fuel? How much more technology is it going to take to do and control? Like today, we've got equipment. Certainly you can hit the moon if you needed to hit the moon. But to get the trajectory just right, with a limited amount of fuel that you have, to get to the right speed, the right angle, the moon's moving, it's orbiting, the Earth is moving. You've got to work all that out. A computer can do that today. But now you have to have the fuel to be able to do it. Plus, it's got to be protected through the Van Allen belts and the whole 9 yards. And what people don't understand is when you get to space, you are just simply out of the atmosphere. You're not out of the gravitational pull of the Earth. You're not even close to it. Like I said, if you took a basketball and you put a dime on top, that's low Earth orbit. That's as far as you are away off the planet at that particular time. The gravitational drop is so little, you'd barely notice it. Considering the fact that the Lagrange zone, the L zone, for the Earth to the Sun is 1 million miles out. And that's when the gravitational pull of the Sun and the gravitational pull of the Earth are equal. And that's 1 million miles out. So if you think you're going to eject off, you're still accelerating from the gravity of the Earth the same as you are taking off. The only thing that's different is you don't have any air drag. There's no atmospheric drag. But when you're 10 miles off the Earth, there's very little atmospheric drag because there's very little atmosphere already. Not to mention the fact that things are rocket, like they're designed like a bullet, so that they have very little drag to start with. But imagine like 10 miles off, and there's basically no air drag on that vehicle anymore. Right? Even at 5 miles off, so you're already down to 5 psi air pressure at the height of Mount Everest. At 5 miles off the Earth, the air drag's dropped down. At 10 miles is virtually nothing to worry about. That's not where the problem is. The problem is still the gravitational pull. And that pull's going to be there until you meet up with the L zone between us and the moon, where it changes. You're always going to be slowing down. To go from 50 to 100 miles to low Earth orbit is 100 times more difficult. How much more difficult is it to do a translunar injection? And I do not believe that any manned mission has ever done that.
Unmanned missions are different.
In the last 20 years, yeah. I wouldn't go back more than 20 years. Because they need the guidance systems.
Yeah, they do.
They have to be autonomous guidance systems, and that didn't happen until 2002. And that didn't happen until 2002.
So
That IBM 750 that they put out.
So what about the lunar orbiter?
We were just looking at the camera that did the lunar orbited mapping.
Yeah.
Yeah.
There are so many questions that arise when you start looking into it as deeply as you've done, as Robert's done. You start looking into it that deeply. There are so many questions that arise. that are reasonable questions. I mean, they're not conspiracy or anything like that. They're just straightforward scientific questions. They're just straightforward scientific questions. If that happened and that happened, how did that happen? It's different.
Why are they just up and running? And that's in Hawaii, by the way, all this testing they're doing for the cratering for a lander. Which means that they're going to be able to put together something that will be able to land on the moon.
Eventually, yes.
Eventually. But they're still doing the testing and the soil samples to see how much cratering there's going to be.
You see, that's what I mean about, they do that now. So the obvious question is, well, didn't they do it 50 years ago or 60 years ago when they were creating Apollo? And if they did, why do they need to do it again?
When Apollo so-called landed, it didn't do anything to create a crater. So why would it be a concern? If all of the excuses that NASA has got about there isn't a crater there. And don't forget, what they're doing testing on is maybe a 6 or 7, maybe 800-pound robotic machine that's going to be landing. What was Apollo? Total weight when it landed, I think it was still, 13,000 or something?
I believe it was about 3 tons, which is, 7,000 pounds.
The takeoff weight was 3 tons. And then you still got the entire frame of the lander.
Plus all the internal support systems.
And those 60-kilo batteries. Those would be the first damn things I'd be throwing out the door. They're used up. Get rid of them. You're going to be, 20 minutes up there to get loaded and gone. Get rid of these 60-kilo batteries and the outer gloves and cameras and everything else.
Yeah, which would be nice to have brought back to Earth, wouldn't it? There's a lot of censorship at the moment. And NASA must be getting very nervous because the longer they take to launch their SLS rocket, it's only been in construction for 12 years, testing it for 5 years. You think they've got it sorted by now. Oh, they've got a hydrogen leak. Why are they using hydrogen? They didn't use hydrogen on Apollo. They use liquid oxygen and kerosene. Hydrogen is the Houdini of gas. It can't be constrained. It can't be restrained. It's so small, it keeps getting out.
Musk is using methane and getting twice the thrust. The ones he's using are 500,000 pounds apiece. The ones on the SLS are 200,000. They're getting all their boost off the solid rocket.
That's right, yeah. Those solid rocket boosters are quite old technology. I mean, they were developed by Jack Parsons 60-odd years ago as jet takeoff assistance for heavy loaded bombers. They put these little solid boosters on the side to get the plane up in the air. So they're using 60-year-old technology. I mean, it sounds all very impressive, and it looks very impressive when it takes off because it produces all this great clouds of whatever it produces. And maybe it works. And the trouble is you can't switch them off. Once those solid fuel boosters are ignited, that's it. They've got to burn out before they'll stop.
Well, you got the other problem. I mean, if you got ones that you can turn off, how are you coming back down? You don't have wings.
And you parachute down. I mean, that's why they have to be rated for human spaceflight. It's all very well putting instruments on board, doesn't matter if it crashes, you can always put more instruments on board, but you've got trained astronauts on board, you've got to ensure their safety. But if they can't ensure their safety, they're not going to fly. I believe in three things: Father Christmas, the Tooth Fairy, and the Easter Bunny. For everything else, I want evidence. And the evidence for the moon landings by humans is sorely lacking.
I was watching Jay Leno interviewing on tour at Elon Musk's facility. Obviously, Elon Musk was saying things that they don't want because the video's been removed.
This is very inspiring, because I was one of those people, I was all into the space race, and then we just walked away from it. And now it's back, and all these kids are here doing this because of you, and you're their inspirations. That's got to feel good.
Yeah, I mean, I think we've got an incredible team, and we're making great progress here. We're trying to achieve the holy grail of rocketry, which is a fully and rapidly reusable rocket. No one has ever made a fully reusable orbital rocket, and never one that could be rapidly reflown like an aircraft. And that is actually the essential sort of invention, if you will, that is necessary to make humanity a multi-planet species.
And it seems like common sense. I mean, you wouldn't get in a plane, fly it once,
yeah,
and then wreck it, and then build
another.
That'd
be insane.
Plane.
Yeah.
So
like,
I
it'd be
mean,
like the current, the way that rockets used to be would be like if you bought a plane and then over your destination you jump out with a parachute and then the plane crashes.
Right.
And that's actually how rockets work.
Why do you think it was not done before?
I mean, it's a very hard engineering problem. You need a lot of advancements on the engines, the airframe, the heat shield, and all of the technologies that go into the rocket, in order to have it be reusable, but still get payload to orbit.
Right.
Getting to space is easy,
right,
but getting to orbit is 100 times harder than getting to space.
Really?
Yes.
Okay.
Confused? Let me try to explain. First things first. It's hard to believe space is just a mere 62 miles above the Earth. Yeah, fewer miles than, say, a round-trip drive to the nearest outlet mall. But what we call low orbit sits at around 100 to 1,200 miles up and is way harder to achieve. Primarily because it takes a lot more propellant to not only get there, but to maintain enough speed to stay up in orbit. And if an object can't maintain a fast enough orbital velocity, it'll eventually fall back into our atmosphere and probably burn up on re-entry. And since the current price for launching a SpaceX Falcon Heavy rocket is $97 million, we definitely don't want that.